the question, why is there something rather than nothing, has been around in one form or another through philosophy and religion for much of human history. What we've discovered, among other things, is that what most people would consider to be nothing is not only not boring, it's actually a very interesting thing, but actually nothing can become something. In fact, nothing can be unstable. Now, what do I mean by that? We've discovered that empty space, which is for most people nothing, you take a region of space and you get rid of all the particles and all the radiation, so there's nothing there. First of all, we've discovered one of the most amazing things is that if you get rid of everything, that empty space actually weighs something. We don't really even understand why, but we have some inklings because we know, because of quantum mechanics and relativity, at a fundamental level, empty space is a boiling, bubbling brew of virtual particles that are popping in and out of existence in a timescale so short you can't see them. Now that sounds like philosophy. It sounds like counting angels on the head of a pin, but it's not. Because while we can't see those virtual particles directly, we can see their effects indirectly. In fact, we can calculate their effects, and they affect the properties of atoms in a calculable way. And including those effects has led to the best predictions in all of science. We can compare our theoretical models with observation and get agreement to 9 decimal places. Nowhere else in science can we do that from first principles, predict something to that kind of accuracy, but we only get the right answer if we include the effect of these weird virtual particles. So as crazy as it is, it's true. Now, because of that craziness, it means that empty space can be endowed with properties we wouldn't have imagined before. We still don't get the right answer when we try and calculate the energy of empty space completely in the universe, and it's a big mystery. It's the biggest mystery in all of science. But we know that it can have weird properties. Now, once you add gravity to the mix, and gravity allows things to have negative energy as well as positive energy, then empty space, in which there are no particles, can spontaneously produce particles because you don't violate the conservation of energy. Afterwards, at the beginning you have zero total energy. Afterwards you have zero total energy. But at the beginning you had emptiness, and afterwards you have a universe full of stuff. And it seems like a miracle. But you don't need a miracle to do it. You just need the laws of nature. And in fact, you're guaranteed that if you wait long enough, empty space will produce particles. And so nothing is unstable. So one of the answers to that question, why is there something rather than nothing, is that nothing is unstable. It'd be far more surprising to find nothing than something in some sense, but we wouldn't be here to ask the question if we did. Now, there are many more fascinating aspects of nothing, because it turns out that you might say, and some people do say, that empty space alone isn't nothing. That after all, where did the space come from? And of course, it turns out, as we've been trying to understand the laws of physics and apply quantum mechanics to gravity, that space itself can be a dynamical object. We know in general relativity, space expands and contracts and bends in the presence of matter. And if you make it quantum mechanical, then even space can pop in and out of existence where there was no space before. So you can create whole universes where there was no universe before. And indeed, in that way, you might imagine creating a universe from literally nothing, no space, no time. And these ideas are amazing and fascinating. And we can't prove that we came from nothing that way, but we can show it's plausible. And the fact that it's plausible, that we can have a set of normal physical mechanisms that take us from no space, no particles, to a universe like the one we live in, which has all the characteristics of a universe we might have expected to be created from nothing, to me is one of those amazing stories one can tell, which is why I just told it.
In the early decades of the 20th century, the discovery of something called antimatter raised a significant problem. This new substance called into question how our matter-filled universe could exist at all. Let me explain. In 1928, Paul Dirac came up with a new and elegant equation to describe how particles, like electrons, behave when they travel close to the speed of light. Surprisingly, Dirac found that his equation always had 2 solutions, sort of how the square root of a positive number always has 2 answers. Dirac recognized that one solution described the electron, but the other, well, that was a mystery which he first dismissed as a mathematical artifact. He later said it took him 3 tortured years to summon the courage to claim that this other set of solutions was describing something real, antimatter. That is, the first solution described an electron, while the second described an anti-electron. The anti-electron would have the same mass and spin as the electron, but it would have an opposite electric charge. Now, since the electron has a negative charge, the anti-electron would have a positive charge, which is why we also call it a positron. Dirac's equation says the same thing is true for all particles. Quarks have antiquarks, and just as quarks can make up protons, antiquarks can make up antiprotons, and antiprotons and anti-electrons, they can make anti-atoms, and so on. Dirac's theory was a remarkable achievement. If proven correct, it would double the number of known particles in the world. Just 4 years later, in 1932, Carl Anderson took this picture of a particle racing through a bubble chamber. His measurements showed that it had the same mass as an electron, but a positive electric charge, the first detection of antimatter verifying Dirac's mathematical prediction. Now we come to the puzzle. When matter and antimatter come together, they annihilate. And this raises a big question. Why is there any matter left? After all, if matter and antimatter are identical except for having opposite electric charge, and since as far as we can tell, the laws of physics don't have a preference for a plus sign over a minus sign, we would expect equal amounts of matter and antimatter to be created at the Big Bang. And then, as they intermingled, the matter and antimatter would all annihilate, leaving a sea of structureless radiation. But if this were the case, the universe as we know it wouldn't exist. So what's going on? Physicists have been puzzling about this for more than half a century. Some have wondered whether the antimatter got separated from matter and might still be out there, existing as anti-planets, anti-stars, anti-galaxies, maybe even anti-universes. Others have imagined that just after the Big Bang, a tiny imbalance between matter and antimatter somehow crept in. Indeed, to avoid total annihilation, scientists have calculated that for every billion antiprotons, there must have been a billion plus one protons. That's a tiny imbalance, but it would have left over just enough matter to make all we see in the universe today. To figure out which, if any, of these theories might be right, scientists are undertaking a range of experiments to understand antimatter with far greater precision. And all this is part of a grand quest to answer a question that is as simple as it is profound. Given that matter and antimatter annihilate, how is it that we exist?
If we talk about the creation of the universe, is there anything in nature which involves creation, where something comes out of nothing? And matter-antimatter is the prime example. That if you switch on an electric field, the electric field pulls an electron one way, it pulls the antiparticle the other way, because they have opposite charge. And so even if you have no particles, if you turn on an electric field, you will create if it's sufficiently strong, you will create a particle-antiparticle pair out of nothing. Creates matter and antimatter in exactly equal amount. The positron, or anti-electron, and the red part, the electron, those are classical parts of this process. Literally just this particle flying off to infinity. The gray part is very quantum. The particle, you see, the particle, if you think about what's going on at that time, it's not going forward in time. It's traveling through space at a fixed time. That's actually not allowed, classically. Okay? Nevertheless, it happens. But so I want to point out that's the quantum part, the gray part. Let's, instead of thinking about two particles, think about one. Because one of the deepest insights which occurred in the 30s and 40s, physicists called Stuckelberg and then Feynman, was that what is an anti-electron? What is an antiparticle? An anti-electron has the same charge as an electron. Why? Because it's actually the same particle. The only difference is that it's going backwards in time. Okay? And so this was a very profound principle. Feynman actually built his whole machinery for particle physics on that insight. And so from that point of view, forget about the antiparticle on the left. Think only about the electron. Imagine I had an electron which went backwards in the external observer's time, but forwards in its own time, which goes along its path, right, then it would have been the anti-electron. It went back in time, went through this quantum region, and emerged as the electron. So that picture is a beautiful mathematical, a very precise picture of how a particle-antiparticle pair is created. Actually, just one particle that's going backwards and forwards in time. So that is the closest analogy we have in nature to the formation of a universe. This is the scenario which we recently proposed, is that the Big Bang was just such an event, where from one point of view, say we're an external observer, we'd say an anti-universe came out one side and the universe came out the other. But that's actually not the deepest point of view. The deepest point of view is that it's all a single thing, and you can regard the left-hand side as going backwards in time towards the Big Bang, just as the anti-electron was the electron going backwards in time, and the right-hand side is the universe going forwards in time. So in a sense, the universe causes itself. You can mirror image this picture, if you like, and it's exactly the same. We could not tell which of these two we lived in.
So where would you put the beginning of the universe in this way of thinking about things?
There really isn't one.
It just is.
You see, the important point is the gray region in that particle picture was quantum. It's not classical at that point. It doesn't satisfy our classical notions of there being a single time, for example. So in this picture, in the middle of the picture, that's the blurry part. That's the quantum part. You shouldn't say, the universe wasn't started by an external agent at a definite time. No, the blurry part is where we don't even know what time is. Okay, so amazingly you can describe all this, just as you can describe with perfect precision the creation of the electron-positron pair. You can describe this, but you need to use quantum gravity. And when you do this, this picture seems capable of producing the matter-antimatter asymmetry in the universe. The U is different than the U bar, but the difference, we see a universe full of more matter than antimatter because we're looking at it going forwards in time. If we were going backwards in time on the other side, we'd see exactly the opposite.
And the God's eye view sees a complete symmetry.
In the God's eye view, there is perfect symmetry in the universe.
I find it very confusing. So if I were living in this antimatter part,
yes,
do I get younger? Can I turn my gray hair back to jet black?
No, you don't. No. So in terms of, you can think about it as one causing the other, but actually when the universe becomes classical, you have to identify the U and U bar. There's no distinction between them. There really is no distinction. So how would I decide if time is going forward? That's the direction in which the universe is getting bigger and which galaxies are forming, and you can see that's the same, whichever side you're on.
Wow.
So there's an antimatter in some way then?
No.
No?
No.
No.
In external time, it would be
the classical
early.
parts of this picture, the U and the U bar, are identical.